Hello, doctor. We are from Group 21, presenting about latent heats of pure substances. First and foremost, me, Ike Ming, will present the history of development. In 1750, Joseph Black studied thermodynamic system changes, like volume and pressure at constant temperature in a thermal bath. Black discovered that melting requires significantly more heat than temperature increase alone, and freezing releases more heat than can be explained by temperature decrease as well. By heating equal masses of ice at 32 degrees Fahrenheit and water at 33 degrees Fahrenheit to 40 degrees Fahrenheit, Black found that water absorbed 7 degrees of heat, while ice absorbed 147 degrees of heat, taking 21 times longer than water. The ice's temperature increased by 8 degrees Fahrenheit as sensible heat, indicating that 139 degrees of heat were stored as latent heat. Additionally, he vaporized an equal mass of water, requiring 830 degrees of heat. Besides, James Prescott Joule defined latent energy as the potential energy arising from interactions among particles.
Next, me, Surika, will present the definition and theories of latent heat. In definition, latent heat is energy released or absorbed by a body or a thermodynamic system during a constant temperature process. When a pure substance is liquefied from the solid state or vaporized from liquid or solid at constant pressure, no change in temperature occurs. However, these processes require the transfer of finite amounts of heat to the substance. This includes latent heat of fusion, latent heat of vaporization, and latent heat of sublimation. In theories and equations, first one is latent heat of fusion, which is the amount of heat required to convert a unit mass of a solid to a liquid at a constant temperature. Next, latent heat of vaporization is the amount of heat required to convert a unit mass of a liquid to a gas at a constant temperature. The equation involves is shown now. The Clausius-Clapeyron equation describes the relationship between pressure and temperature during a phase change and phase equilibrium between two phases. The equation is shown on the slide. The next two slides explain about the thermodynamic identity for latent heat and the temperature dependence of latent heat. The thermodynamic identity for latent heat uses the Gibbs free energy and the concept of entropy. Kirchhoff equation is used for temperature dependence of latent heat. Lastly, we'll be showing a few examples of a mathematical calculation based on our topic using MATLAB. The first example question is shown now. Feel free to pause the screen to see the solution better. Second example is now being shown. Third example is now being shown. Fourth example is now being shown. In our 3D model we created, when ice at 0 degrees Celsius is heated, it absorbs energy, which is latent heat of fusion, without a change in temperature, causing the ice changes into liquid water. After melting, when water is further heated to 100 degrees Celsius, it begins to change into vapor. The energy absorbed in conversion of liquid water into water vapor without a rise in temperature is the latent heat of vaporization. Both latent heats are energies absorbed during phase changes in constant temperature. That's all from. Thank you.